to send you a reminder email. For you, Matt, it doesn't give me the option. I don't know why. Jason, I already gave you permission, and the same with Matt, it doesn't give me the option. Is there anyone else? Please raise your hand if you are not allowed to record.
I'll try and leave and come back. Maybe that'll work.
Okay. All right, let me, for you the same. For some of you guys, it doesn't give me the option. Okay, raise your hand if you are not allowed. Success, it doesn't give me the option. All right. Anyone else? Raise your hand if you are not allowed to record. Matt, it still doesn't give me the option. Do you have iPad? The same for you.
I'm on my phone at the moment because I'm
maybe that's
not
going
home.
on. Yeah.
Are you able to send out the recording maybe?
I'm gonna send out the no audio version, you know, the slideshow, but I'm gonna record, and if the capacity of the email allow me, I can send it, or if I can zip it somehow, you know.
Okay.
Okay, let's start. Let me start in 1 or 2 minutes. I'm waiting for, because I don't want, once on share, I don't want to go back to. Is there anyone who is not allowed to record? All right. So I'm going to share my screen with you guys. We are going to start. Please have a piece of paper because we are working this together. I don't want just, you know, explain. I want to get you thinking. In the first example, a 10 kilogram mass of superheated refrigerant. So it already tells us the state. So it's 10 kilogram mass of superheated refrigerant at 1.2 megapascal and 70 degrees centigrade is cooled at a constant pressure until it exits at a compressed liquid at 20 degrees centigrade. In part A, show the process on a TV diagram. Oh, I forgot to record it myself, or did I? Let me, I don't know how I can go back. Let me stop sharing. And let me check. I haven't recorded yet, so I have to start all over. Okay. Okay. Can you see my screen?
No.
All right. Okay, I'm going to start. The first example, a 10 kilogram mass of superheated refrigerant at 1.2 megapascal and 70 degrees centigrade is cooled at a constant pressure until it exits as compressed liquid at 20 degrees centigrade. In part A, we want to show the process on T new diagram. Part B, we want to determine the change in volume between state 1 and state 2. And part C, we want to find the change in total internal energy. Sometimes, you know, when they put it in the steps, it's like a guideline. You know, so you have to do, you know, A first and B the second, and then, you know, the next steps. I'm not sure about this one, we will see, but sometimes it's like, you know, a hint or guide. Okay, let's start with part A. Show the process on TV diagram. So you start with superheated, the substance is refrigerant, and the first state is superheated. The pressure and temperature is given. The pressure 1.2 megapascal, the temperature 70 degrees centigrade, and it's cooled. And in the second state, it is compressed liquid, and the temperature is given, just the temperature. I give you 2 minutes to show it on a TNU diagram. It's already there, but I want you guys to do it yourself. Then when I explain, you can absorb it better. So guys, please make sure you are mute unless you have a question or you want to answer. But, you know, during this session, I'm not asking you any question. I just give you some time to do it yourself, and then I'm going to explain. All right? So show the process on TNU diagram. By the way, when it's TNU, you keep the pressure constant on the diagram. It was P nu, you keep the temperature constant. So when it's TNU, it's this ascending diagram, and you keep the pressure constant along this diagram. Two minutes. Here I listed the noun at the state 1, temperature and pressure. At the state 2, the temperature and pressure, because pressure remains constant. And also the state, which is given. Sometimes you have to figure it out yourself. But in this case, it's already given. Okay, now I'm going to explain. See, it says that it's superheated, and you know, at constant pressure, right? At a constant pressure. When pressure is constant, it's T. You take the y-axis at temperature, and x-axis can be anything, but in this case, it's nu because it asks us T nu, right? So you have this for when y-axis shows temperature and pressure is constant, it's this ascending diagram. So this part is related to compressed liquid, right? So the temperature rises and reaches the saturation temperature for the given pressure. And then here is saturated liquid, here is saturated vapor, under the dome is saturated mixture, and here is superheated. So it's superheated. So we are somewhere here on this line. That's the state 1. And then under the constant pressure, it cools down, meaning the temperature drops. All along this diagram, the pressure is constant, 1.2 megapascal. So pressure drops, right? And at some point, it reaches 20 degrees centigrade, and it's compressed liquid. Because it's compressed liquid, you have to be on this line. And somewhere on this line, when the temperature is 20 degrees centigrade. So you have this 20 degrees centigrade, the intersection of that with this line, which is for compressed liquid, that's a state 2. So here is how it happens. A state 1, and it goes to a state 2. And all along, pressure is constant, right? That's part A. Now, in part B, it asks you to determine the change in the volume. So during this process, as you see, when you are at a state 1, here is a specific volume. When you are at a state 2, here is a specific volume. So as you go from a state 1 to a state 2, actually the volume decreases. Whatever the trend, whatever happens to, you know, a specific volume happens to volume 2. For example, if volume triples, a specific volume triples, right? Because it's the same mass. And, you know the relationship between mass, volume, and a specific volume. Volume divided by a specific volume is mass. When mass is the same between a state 1 and a state 2, then, whatever happens to a specific volume happens to volume, because volume divided by specific volume is mass. Now, you need to find the volume at state 1 and volume at state 2 and subtract these two. So I give you 2 minutes to think about that. Of course, 2 minutes is not enough, but I want just to give you some time to analyze that. And then I'm going to explain how you are going to do that. Calculate the change in the volume going from state 1 to state 2. The hints would be, find the relationship between specific volume and volume maybe, or I prefer not to give you a hint. 2 minutes. Find the relationship between volume and specific volume. How you can calculate volume if you have mass and a specific volume. Because going from a state 1 to a state 2, mass doesn't change. It is the same mass, 10 kilograms. So you have mass. If you have relationship between mass and a specific, volume and mass and a specific volume, maybe you can calculate volume in each state. Okay, let's go ahead and do that. Part B. We need to calculate change in the volume here. Let me move it a little bit. Change in the volume is volume at state 2 minus volume at state 1. That's what we need. See, guys, always spend some time to analyze the problem. Never rush into the solution, not just in this course, not just for this problem. When you are doing a project or solving a problem, take some time to analyze. Half of the time you should analyze it. Do not rush into the solution, because that's just waste of time. Okay, delta volume, change the volume is volume at state 2 minus volume at state 1. All right. What is the relationship between volume and a specific volume? Volume is mass divided by density. It's m over rho. In other words, it's m multiplied by 1 over rho. What is 1 over rho? That is called a specific volume. That's a reciprocal of density. Volume per unit of mass is called a specific volume. That's 1 over rho mathematically. So nu is 1 over rho. So we know volume is mass divided by rho, or mass multiplied by 1 over rho, or mass multiplied by nu, because 1 over rho is nu. So m times nu is volume. If you want to memorize it, you can memorize it this way. Volume divided by specific volume is mass. So volume is mass times the specific volume. So between state 1 and 2 is the same mass. So at state 2, the volume would be m, which is 10 kilogram, times nu2, specific volume at state 2. At state 1, volume 1 would be the very same mass, 10 kilogram, multiplied by a specific volume v1. So you can factor out m, and it's m nu2 minus nu1, right? These are a specific volume. You can get it from the table based on the state of the substance. Here I mentioned volume is mass divided by density, and this guy is nu, so it's m nu, or volume divided by nu is m. So the question is, I have mass. If I want to calculate change in the volume, I need to get these two from the table. So what are the values for nu1 and nu2? So I know state 1 is given. Sometimes you have to figure it out based on the information. You need two pieces of information to determine the state. Sometimes it's temperature and pressure. Sometimes it's temperature and or pressure and the value of one of the properties like nu or h or u. You need two pieces of information at least. So in this case, we know the state 1 is superheated vapor, and we know the substance is R134. So because it's superheated, the table for that, for refrigerant superheated vapor is A13. SI system, it's on page, my edition, 920. The temperature and pressure is given. We know how superheated tables looks like. They're common in section. Each section is related to a given pressure. Find the section which is related to 1.2 megapascal. In that section, the very first column shows the temperature. Go ahead and find 70 degrees centigrade. Sometimes you cannot find it directly in the table. It lies between two rows and you have to interpolate or estimate. In this case, you can. So in this section, 1.2 in the first column, find 70, go ahead. There are three columns, one for nu, one for u, one for h, and read the value for nu, which is this, 0.019502. The unit is meter cubic per kilogram. That's volume per unit of mass. For nu2, you know that's compressed liquid. So the correct table would be compressed liquid table, which is very, very much similar to superheated table. But the thing is, sometimes it lacks some data. The reason is for compressed liquid, you know, the value of properties like U and H and nu, they are not very dependent on pressure, but they are dependent on temperature. So when you cannot find this pressure in the table, it lacks data, you are going to estimate the value of that property for compressed liquid with value of that property with saturated liquid. Let's go back and show it on diagram. In this diagram, see, it is compressed liquid. So what you have to read for nu is this value, right, for compressed liquid. But you cannot find it in the table under this pressure and temperature. What you do, you estimate this value with value of nu F, which is the value of nu for saturated liquid instead of compressed liquid at the given temperature, which is 20, not given pressure, because there are two types of saturation table, the one that starts with pressure, you can find it, the one that it starts with temperature, but you go with temperature because for compressed liquid, the value of this property is insensitive to pressure, just sensitive to temperature. So you go ahead to saturated table, which will start with temperature. In the first column, you find 20 degrees centigrade because temperature is 20 degrees, and you find nu F, and that's your nu2. Basically, nu2 is value of nu for compressed liquid, but you are estimating that with value of nu for F, saturated liquid. So that's going to be table A11. A11 and A12 are saturated table for refrigerants, 134A, but A11 starts with temperature, A12 starts with pressure. That is on page 916. If you do that, you get nu2, which is nu F at given temperature, not given pressure. Keep that in mind. If you are estimating value of property for compressed liquid with value of that property for saturated liquid, you just use the temperature at the given temperature and pressure. So you get this value, 0.008116 meter cubic per kilogram. Then you have You just plug in into this equation. You have value of nu2, a specific volume at state 2. You have value of a specific volume at state 1, and you have mass. You just plug everything in, and as you expect, and I'll show you on diagram, the volume decreases like a specific volume, and you get minus 0.187 meter cubic. That's a change in volume. Now part C. Let's go back and see what part C asks us. Part C asks us about find a change in total internal energy. Lowercase u shows internal energy per unit of mass. So the change in internal energy going from a state 1 to a state 2, now you have to take x-axis at u. So here is u1, here is u2. So change in internal energy is u2, lowercase u, minus u1, lowercase u. u2 minus u1, that's change in internal energy per unit of mass because u is lowercase. If you need change in total internal energy for the whole mass, you have to multiply by m. So here is part C. Change in internal energy, and that's capital U for the whole mass. Mass times u2 minus u1, right? So it is, you have to get u1 and u2 from table. The very same way you got nu1 and nu2. For u2, because it lacks data, you cannot find the given pressure 1.2 megapascal in compressed liquid table. You are going to estimate it with UF, value of that property for saturated liquid at the given temperature, which is 20 degrees centigrade. And U2 is 78.85 kilojoule per kilogram based on the table, saturated table for refrigerant, which is table A11, the one that starts with temperature. And U1, it is superheated. We refer to superheated vapor table, that is table A13 for refrigerant 134A. That is on page 920. You go to the section with pressure 1.2 megapascal in the first column, find 70 degree. And there are 3 columns for U, for H, and nu. You go ahead and read U, which is your U1, which is 277.23 kilojoule per kilogram. So delta U, change in internal energy, would be M, the total mass multiplied by, this is delta lowercase u, which is change in internal energy per unit of mass. So the change in total internal energy, which is decreased, U2 is less than U1, is minus 1,984 kilojoule. All right? Can you hear me right? I need to check, double check.
Yes.
Yes, we can.
Okay,
Yes.
good. Okay, good. Is there any question before I go to the next one?
Can you just give 1 minute to, okay,
Yes,
Oh,
just one.
you need
What
more
was the
minutes?
table
Okay.
you used
just to
again
copy
when
down.
you get-
All right.
Sorry.
Guys, please make sure you are muted. It's a large class and it's not fair to other students if you are not muted.
I just have one question.
Yes, please. You have a question?
Professor, I
If
have a
you have
question.
que-
Yes.
yeah,
What was the
please.
table used again for? Can you hear me? What was the table
Yes,
used
I can.
again for U2?
For you too, because it is compressed liquid and you cannot find data in compressed liquid table, you go back to saturated table because you want to estimate the value of that property, which is U or nu, with UF or nu-F, which is value of that property for saturated liquid. So you go back to saturated table for refrigerant 134A, that is table A11. A11. A11 and A12 are for refrigerants, and those are saturated table. The very first one, A11, starts with temperature. The second one starts with pressure, all right?
Thank you.
Sure. Let's go to the next one. Water in a large lake is to be used to generate electricity by installation of a hydraulic turbine at a location where the depth of water is 50 meters, that's H, the difference between the free surfaces of 2 lakes. Water is to be supplied at a rate of 5,000 kilogram per second. That is mass flow rate. If the electric power generated is measured to be 1,862 kilowatt, that is the power, the power of electrical power, basically. The generator and the generator efficiency is 95%. That is efficiency eta. We use eta for efficiency. Generator. We want to determine the overall efficiency of the package, which is turbine generator. That's part A. In part B, that's one of those examples that when they put it in parts A, B, C, it guides you. It's like a guideline. It's like a hint. Part B, the mechanical efficiency of turbine. And part C, the shaft work supply by turbine to generator. I give you a few minutes and just focus on part A. What is the overall efficiency of the whole package, turbine generator? Please list all the noun like difference in elevation between fluid surfaces and also mass flow rate, crossing the turbine, and also electric power, generated by generator, right? Which is 1,862 kilowatts. That's power output of the generator and also efficiency of the generator. In part A, you want to calculate the overall efficiency of turbine generator. I give you 2 minutes. It's not enough, of course. I just want you guys to think about that and set up the equation. Okay, here are 2 legs. See the difference between the elevation, 50 meter, that's a power out by generator. There is a turbine, right? The fluid works on the turbine and turbine extracts energy from the working fluid. So the mechanical energy of the fluid at the output of the turbine is less than the input. And when it extracts that energy, it converts it to this shaft power, mechanical power, which is output of the turbine. That goes as input to the generator, and generator generates electricity, and that's the power output. Here it is. And we have the efficiency of generator here as 95%. Let's move this a little. And mass flow rate crossing the turbine is 5,000 kilogram per sec, right? So part A, it asks you to calculate the overall efficiency. So if you take turbine and generator as a whole package, you are looking for overall efficiency or efficiency of turbine generator. That's the output of the whole thing, the whole package, which is electric power, right? That's W dot. Here is W dot out, electric power. And what is the input to this package? The input is the energy that turbine extract from fluid, working fluid. That's basically change in mechanical energy of the fluid, and everything expressed in terms of rate, in rate. So that is the rate of change of mechanical energy of the fluid. And we use the absolute, that means absolute value, because we know that term is negative. the change would be negative. The mechanical energy at the outlet is less than inlet. That's why we use absolute for absolute value, right? So see what we have here, because we are looking for overall efficiency. We have the output of this package, which is electric power. We have this check mark. We need to calculate a rate of change, rate of change of mechanical energy of the fluid. I taught you how to calculate mechanical energy of the fluid, and I also show you where it comes from. It's out of the scope of this course. It's fluid stuff, but that's the energy of the fluid, okay? So that comes from energy equation. So here is the formula that we derived in the class. That's chapter 2. That is m dot, right? And here is the term in the brackets. That is mass flow rate. M dot is mass flow rate crossing the turbine. That is P2 minus P1, change in pressure before and after turbine, divided by density of the fluid, plus half of V2 square minus V1 square. That's a change in velocity before and after turbine, right? Plus G, which is gravitational acceleration, time change in elevation before and after, right? You can also rewrite it this way, because mass flow rate is density times volume flow rate. You keep volume flow rate, multiply mass flow rate by the term in the bracket. So rho cancel out. So it's P2 minus P1 plus half of it, rho here. It's half of rho because you are multiplying by rho, keep volume flow rate outside. So it's rho V2 square minus V1 square. And when you multiply rho by G under the note I wrote, rho G is called gamma. And gamma, as I explained in chapter 1, that is a specific weight. That is weight per unit of volume, because rho is density. That is mass per unit of volume. When you multiply by G, that becomes weight per unit of volume, which is called a specific weight, gamma. So rho G, it's gamma times Z2 minus Z1. So you can calculate it either way. So we have mass flow rate, right? And you have changing, let me go back and see what we have here. Okay, sorry, I wanted to go back. See, you can calculate it between inlet and outlet. And also, if we assume that there is no friction in this pipeline, instead of calculating the change in mechanical energy between inlet and outlet of turbine, you can go between these two free surfaces. But we are under this assumption that there is no friction, there is no losses, waste of energy in this pipeline. Then change of mechanical energy between inlet and outlet is the same as between these two free surfaces, because we know nothing about this turbine, so we cannot calculate between these two. So we go between these two free surfaces, and here velocity is 0, here velocity is 0. So these two are 0. And here it's exposed to, on top of this, pressure of atmosphere, on top of this pressure atmosphere. So this is 0. And there is only change in elevation, right? Z1, Z2 minus Z1, which is 50. So basically it's M dot, this term goes away, this term goes away. It's M dot G Z2 minus Z1. So we have M dot here, M dot G Z2 minus Z1, which is H, which is 50 meter. Make sure units are consistent, 50 meter, G is 9.81 meter per second square, and M dot 5,000 kilogram per sec. You plug everything in, you get 2,455 kilowatts, right? And that is rate of change of mechanical energy. Once you have that, you just plug in into this equation. Overall efficiency is the total output of the package, which we have, that's electrical power. That generator generates 1,862 kilowatt divided by rate of change of mechanical energy of the fluid, which is 2,455 kilowatt. Plug everything in, you get 0.76, which shows that overall efficiency is 76%. Done with part A. Now part B. part B, it asks us to, let's go back and see what is part B. The mechanical efficiency of the turbine. Now it's focused on just turbine. We have the overall efficiency and we need efficiency of turbine. Let's go back. We know that if overall efficiency, by overall efficiency, we mean efficiency of the whole package, which is efficiency, that's eta, which is efficiency of turbine generator, which is efficiency of turbine multiplied by efficiency of generator. We are looking for efficiency of turbine, and we have check mark means we have the value of this. We have efficiency of turbine generator, and we also given the efficiency of generator, right? Efficiency of generator, 95%, the overall efficiency, we already calculated in part A, plug in, and you can calculate the efficiency of turbine, which is 0.8, it's 80%. So see, putting it in steps helps you to calculate this part. It could, originally ask you what is the efficiency of the turbine, and you have to first do this step and then go to part B. Yes, Peter, do you have a question?
Yeah, quick question before you move on.
Yes, go ahead.
For part A, so since the velocities were zero, the pressure was at zero, we're just looking at gamma times Z2 minus Z1. The reason why we just reverted back to the original potential energy, because we're not given like so if we had different heights, for example, instead of the height difference is 50 meters, then you would use Z2 minus Z1. Is that correct?
See, your question is if we have different height. See, it is Z2 minus Z1 basically, right? So change in elevation. So change in potential energy is the only change that we have in mechanical energy of the fluid, right? Because you are comparing these two free surfaces. Basically, what you have to do, you have to go between inlet and outlet of turbine, but the specification of the turbine is not given. So with this assumption that there is no waste of energy or loss or head loss in the pipeline, instead of calculating difference in mechanical energy between inlet and outlet, you go between two free surfaces, and velocity on both, free surfaces are zero, and also they are exposed to pressure of atmosphere. So P1 minus P2 0, V1 square minus V2 square 0. So the only term in the bracket, which is non-zero, is just change in elevation, and you have to multiply that. It's G delta Z basically, multiplied by M dot. So that is, rate of change in potential energy. And it's delta Z basically. In this case, it's 50 meter, right?
Okay, thank you.
Sure. Let's go to part C. I forgot what part C was. Let's go back and see what is part C. Part C asks us to calculate the shaft work supplied by turbine to generator. See, here on this figure, we are looking for this shaft work. Shaft work is the output of the turbine, which is input to the generator, right? Input to the generator. So there are two ways that you can calculate this shaft work. You can go with generator and write, that efficiency of generator is output divided by input. We have the output, which is electric power, and input is unknown to be determined. And we have efficiency of generator. So the only unknown is the shaft work, which is the input to generator. If you focus on generator and use the formula for efficiency of generator, or you can go with turbine and write the efficiency of turbine, because now we have efficiency of turbine, right? We already calculate that. And efficiency of turbine is desired output divided by input, and the output is this shaft work, which needs to be determined, let it be, and you have efficiency. And so this is output divided by input, which is change in mechanical energy of the fluid that we already calculated in part A. So here in part C, if you go with turbine and use the formula for efficiency of turbine, as I explained, you can go with generator or turbine. Efficiency of turbine is output of the turbine, which is the shaft work out. We are looking for this divided by the input, which is change in mechanical energy of the fluid. So the power of the shaft is efficiency of the turbine multiplied by rate of change of mechanical energy of the fluid. That's part A. That's part B. You just multiply point A by 2,455 kilowatt, which is change in mechanical energy of the fluid, and you have power out of the turbine, which is the mechanical power or shaft power, which is 1,964 kilowatt. Done. Question? Yes, Chirag, please
Yeah,
go
so
ahead.
if you do it with the generator, you would do 1862 kilowatts divided by 0.95, right?
See, the efficiency of the generator is the output of generator. What was the value of output of generator? Yeah, which is the electric power divided by the input, which is shaft power, which we don't have, and set it equal to efficiency of generator, which was, what was the efficiency? 94
95.
something?
Was it
Yeah,
95%?
yeah, yeah. It's a way to go. The next question, it's related to oil pump. So the previous one was generator, this is pump. And oil pump is drawing 44 kilowatt of electric power because we know pump is consuming energy and transfer that energy to fluid by increasing the pressure. Actually, the motor of the pump is using that electric power. An oil pump is drawing 45 kilowatts of electric power while pumping oil with density 860 kilogram per meter cubic at a rate of 0.1 meter cubic per second. Let's move this. The inlet and outlet diameter of the pipe is 8 centimeter and 12 centimeter respectively. If the pressure rise of oil is measured to be 500 kilopascal, and motor efficiency is 90%. We want to determine the mechanical efficiency of the pump. Look, here is the motor, here is the pump. The motor consumes electric power, which is given at 44 kilowatt. When it says pump consuming, or we supply this power to the pump, we mean to the motor, right? And motor uses this input, we supply that to the motor, electric power, and the efficiency of the motor is 90%. And the output would be the shaft work, which goes as input to the pump. And pump use this input, and it has some efficiency, not 100% of the input will be transferred to the fluid, but a percentage of it, according to efficiency of the pump, will be transferred to fluid by increasing the pressure, mainly the pressure, and sometimes the velocity and elevation too. In this case, the velocity changes too. So I give you a few minutes to think about that and try to set up or construct the solution. Of course, a few minutes is not enough. I know that, but at least, get you thinking. And then I'm going to explain myself. There are 2 students raising their hand. Do you have a question?
Yeah, I have a quick question.
Yes, please.
Are these figures given on the exam, or should we be
Yes,
able to
yes.
derive
Mhm.
these?
If it's diagram or something, they may ask you, but for the figure, yes, I give it. Either I give it in the exam.
Thank you.
Sure.
Going to be handwritten like these?
What's that?
Are the exams going to be handwritten like this?
I used to type the exam, but maybe handwritten, I'm not sure. If I have time, I'm going to type it. Otherwise, handwritten. But you're pretty familiar with my handwriting, aren't you?
I'm just
So-
asking because of all the symbols.
Yeah. So I'm not sure if I have time, I will type it. I used to type it previous semester, but if I don't have time, it's just handwriting. But if you have any question, you can ask me, Yeah,
Thank you.
sure. So list the noun and unknown. We're looking for efficiency of the pump. You have the inlet. You have the efficiency of the motor. So maybe you can calculate the output of the motor, which is the input to the pump, right? And go back to the definition for efficiency, which is desired output divided by the input. You have the value of the input. And desired output is change in mechanical energy of the fluid. And if you can calculate change in mechanical energy of fluid between inlet and outlet of the pump, that's the output, desired output, and you have the input. So you can divide and calculate the efficiency of the pump, right? So let's do that. Here, look, let's list all the noun and unknown. We have volume flow rate, right? Passing through the pump, given as 0.1 meter cubic per sec. That's oil. The density of oil is less than water. For water is 1000 kilogram per meter cubic. That one is 860 kilogram per meter cubic. The electric power supply to motor is given at 44 kilowatts, and the efficiency of the motor 90%. Efficiency of pump is to be determined. And we have diameter of inlet, I for inlet or for outlet, diameter of the inlet and outlet of the pump as 8 and 12 centimeter. And the change in pressure between inlet and outlet of the pump is 500 kilopascal. So you have change in pressure. We know the main job of the pump is increasing the pressure of the fluid, right? That way you can, for example, draw water from lower elevation and transfer to higher elevation, because pressure gradient is the driving force for flowing fluid. So let's go back to the definition for efficiency. And we know efficiency, or ETA, is desired output. One of you guys is not muted. Please make sure you are mute. Thank you. So efficiency, ETA, is always desired output divided by the input, right? So for the pump, the desired output, let's go back. The desired output is change in mechanical energy of the fluid, because the job of the pump is transfer, it has efficiency, it has an input, and percentage of that input will be transferred to the fluid. So transfer that energy to the fluid and increase the mechanical energy of the fluid by increasing the pressure, mainly the pressure, sometimes the velocity, sometimes the elevation as well. So here, efficiency of the pump is, the useful pumping power. Remember I talked about useful pumping power? Useful pumping power is the same as change in mechanical energy of the fluid, because, only that part of power that will transfer to the fluid by increasing the mechanical energy of the fluid, that part is useful pumping power of the pump. So useful pumping power of the pump is the output, and the input is, the shaft power, which is the output of the, let's go back, see, the input, which is shaft power, that is the same output of the motor. So you have input to the motor, you have efficiency of the motor, Efficiency of the motor is output of the motor, which is power of the shaft divided by input to the motor, which is electric power. You have efficiency of the motor, multiplied by electric power, that gives you the output of the motor, which is the shaft power, which is the input to the pump. So the very first step would be you multiply the efficiency of the motor by the input of the motor, which is electric power input, and that gives you the power output of the motor, which is the power goes to the pump, the shaft power that goes to the pump as the input. So the efficiency of the motor is 90%, like 0.9, and the electric power 44 kilowatt. So the output of the motor is 39.6 kilowatt, which is the input to the pump, which is the shaft power, which goes to the pump as input. So we just calculated this part and we are looking for this. So let it be. The next step would be calculate the useful pumping power, which is change in mechanical energy of the fluid. So useful pumping power of the pump is the same as rate of change in mechanical energy of the fluid. That's what is called useful. Okay, so and you know how to calculate rate of change in mechanical energy of the fluid. That's m dot, which is mass flow rate crossing the pump multiplied by the term in the brackets, which shows change in mechanical energy of fluid per unit of mass. So it's P2 minus P1, change in pressure between inlet and outlet of the pump, divided by rho density of the fluid plus half of V2 square minus V1 square. These are velocity between inlet and outlet, and plus G Z2 minus Z1. There is no change in elevation, negligible change in elevation. There is no mentioning of it between inlet and outlet of the pump. So this term goes away. But the velocity, because if the pump has the same cross-sectional area at the inlet and outlet, there were no change in velocity because the same volume flow rate crossing inlet will cross outlet, but else it can go. As long as area doesn't change, because volume flow rate V dot is velocity times area. And as long as area doesn't change, velocity doesn't change, velocity of the fluid. But if a cross-sectional area of inlet and outlet is different, then velocity of the fluid would be different. So here's what you should do. We know volume flow rate is VA. So V1, or velocity at the inlet of the pump, would be volume flow rate crossing the pump divided by area of the inlet, 1 for inlet, 2 for the outlet. We assume that it's circular, so it's pi over 4d square. We have the diameter as 8 centimeter, which is 0.08 meter. So you just plug everything in. It should be a square, not cubic. And we have volume flow rate crossing the pump, plug it in, we have V1. The same way, you can calculate V2. Velocity is always volume flow rate divided by area, because volume flow rate is velocity multiplied by area. So V2, or velocity at the outlet of the pump, just give me finish this, and then I'm going to take questions. So V2 would be volume flow rate crossing the pump divided by A2, and A2 is area of the outlet, which is pi over 4d square. So we divide 0.1 meter cubic per sec divided by area of the outlet, and that gives you velocity of the outlet. So we have V1 and V2, and as you see, velocity 1, or velocity at the inlet, is 19.9 meter per sec. And although the same volume flow rate crossing the outlet, because the area changed, and actually there is expansion in the area, it goes from 8 centimeter diameter to 12 centimeter, there will be drop in velocity, decrease in velocity. So velocity decreased from 19.9 to 8.84 meter per sec for the outlet. So here you just plug in for V1 and V2, and this term goes away. There's no change in elevation between inlet and outlet, and we have P1 minus P2. It's given, it was 500, right? And you just substitute rho, or you can go because volume flow rate is given, right? It's volume flow rate, 0.1 meter cubic per sec. So you can use the other version of change in mechanical energy of the fluid. So m dot or mass flow rate is volume flow rate times density, and you just keep volume flow rate, outside the bracket, which is 0.1, and multiply density by the terms in the bracket. So it's going to be just P2 minus P1 because rho cancel out, and we are going to have a rho here, right? And we are going to have rho G, which is gamma. So, I forgot about gamma here. So you have to put, all righty. It's not, when the way it has to be gamma. I forgot about gamma here because it's rho G, right? Rho G, and this should be half of V2 square minus VR square. So I messed up here. You just plug in, forget about this, but just plug in for V2, V1, and V2 and V1. And once you do that, plug everything into this equation. Forget about this part, just plug in into this equation. This is the equation. Then you are going to have rate of change of mechanical energy of fluid being equal to 36.3 kilowatt, right? Is there any question? One of you guys have question? I haven't let me finish this. So once you have useful pumping power, which was changing mechanical energy of the fluid, rate of change of mechanical energy of the fluid, you just plug in the main formula, which was efficiency for the pump, which is useful pumping power or change in mechanical energy of the fluid, which just calculated 36.3 kilowatt divided by the input, which is, shaft power, which we calculated using the motor and input to the motor and efficiency of the motor, which was 39.6 kilowatt. So for the efficiency of the pump, you get 91.8%. Please check to see if this is correct, but you have to plug it into this formula here, right here for V2, for V1. This term goes away, this term goes away, right? There is no change in elevation. We have V1 and V2. So this is multiplication, basically, not just, because sometimes I'm thinking something and it's just writing down, talking. So I just messed up. This is, this goes away. We have this term, the other version, which is, volume flow rate here. And then density multiply. So this cancel out. So here is P2 minus V1, which is 500. And you have half of, V2 square minus V1 square here, multiply by density, which is 860, kilogram per meter cubic. That is the density. It has to be multiplication. The rest is, so this is multiplication. When you plug in, you have to multiply this by that. This is the same version of this. We just, divide m dot and write it as density times volume flow rate. This is the same. This is the volume flow rate, and we multiply density by this term, and this is multiplication. Is there any question, guys? Is everything clear? I see two students raise their hand. Please go ahead, one of you guys. I cannot see your name. Please go ahead.
Yes, Professor. In the previous slide, this was trying to find the velocity at the inlet, or is that the volume?
Here in this essay, we are
yeah.
trying to find the parameter which is important for us in order to find, the efficiency of the pump is change in mechanical energy of the fluid, which is useful pumping power. In order to do so, because the change in mechanical energy of the fluid obeys this formula, in order to do so, we already have P2 minus P1, and we know this term is there. We need to find V1 and V2. In order to find V1 and V2, which are our velocity at inlet and outlet of the pump respectively, we have to divide volume flow rate crossing the pump by the area of the inlet, which is A1, to get V1 or V at the inlet, velocity at the inlet, and one more time, divide volume flow rate crossing the pump, which is 0.1 meter cubic per sec, by A2, which is area of the outlet, to get V2 or velocity at the outlet of the pump. Yes.
I see. Thank you.
Sure. Is there any other question, guys? All right, then. Let's do this one. There's a tank whose volume is unknown, and it's divided into two parts. Yeah, two parts. And there's a partition. One side of the tank contains 0.03 meter cubic of refrigerant 134A, this part. And the other side, and the pressure is given. The pressure is 0.9 megapascal. And the other side is evacuated, okay? And then we remove this partition and the refrigerant fills the tank, and the final state has the temperature of 20 degrees centigrade at 280 kilopascal. And we want to determine the volume of the tank. So what we have is a state one, right? In a state one, it tells us that we know that substance, the refrigerant 134A, right? And let me see, because the final state, it doesn't tell us about the final state, what that is, but about the state one, we know it's saturated liquid, it's given. Sometimes, as I said, you have to figure it out. In this case, it tells us it's saturated liquid at state one. And the volume is given, right? 0.03 meter cubic. And the pressure is given, 0.9 megapascal, right? It's saturated liquid. Then this part is evacuated, and then you remove this partition, and this mass, occupies the whole volume, and basically it goes from a state one to a state two. In state two, it occupied the whole volume, and then pressure becomes 280 kilopascal, and temperature becomes 20 degrees centigrade, which is equal to 293 Kelvin. And we are looking for the volume of the tank. This is an interesting question. I give you a few minutes to analyze that and try to figure out where you should start, what you are looking for, where you should start. All right? Just a few minutes. How we calculate the volume? There is a relationship between mass and a specific volume, right? There is a relationship between mass and a specific volume. Between state 1 and 2, do you agree that mass doesn't change? It's the same mass, right? State 1, it's in this partition. And then when you remove in this part, when you remove this partition, it occupies the whole thing, but it is the same mass, right? And we can calculate mass at state 1. And if I have mass at state 1, I have mass at state 2 because it is the same mass. And if I have mass, let's assume that I have mass. Somebody gives me the value of mass. I have mass at state 2. Can I calculate the volume at state 2, which is basically the volume of the tank? Because this part occupies the whole tank. So basically volume at state 2 represent the volume of the tank. So if I able to calculate volume at state 2, that's the volume of the tank. And I can calculate the volume. I know volume divided by a specific volume, which is nu. Volume divided by nu is mass. So volume is mass multiplied by a specific volume. And if I have mass, and if I have a specific volume at a state 2, I can multiply these two, and I have volume at a state 2, which is volume of tank. So the whole thing is, let's find mass of this refrigerant, which is the same at the state 1 and 2, and let's find a specific volume at a state 2. And a specific volume at a state 2, in order to do so, we need to determine the state, what that is. What is the state? And refer to the table, correct table. And based on these two pieces of information, which is pressure and temperature, I can get a specific volume at a state 2. How I can calculate mass, because I know mass multiplied by specific volume gives me volume at a state 2. Mass at a state 2 is the same mass at a state 1. At a state 1, I know it's saturated liquid. I have this piece of information. Can I use it to calculate mass? Okay, again, just give me, yes.
How did we know at state 1 that it was a saturated liquid?
That's given. That is given.
That's given. Okay, cool.
That is given, yes. Sure. So in a state 1, I need to calculate mass. Okay, again, mass is volume divided by a specific volume. A volume divided by a specific volume. I have volume. If I can get a specific volume at a state 1, I'm done. Divide volume by a specific volume, and I have mass. And if I have mass at a state 1, it's the same mass at a state 2. If I have mass at a state 2, and I have nu at a state 2, I can calculate volume as a state 2, which is volume of the tank. So let's do this. Let's start with a state 1. It is saturated liquid, and the substance is refrigerant 134A. I have to go, and pressure is given. I know it's saturated liquid, so I have to go to saturated table, the one that starts with pressure, not the one that starts with temperature, because I have this piece of information, pressure. Based on the pressure, go to the saturated table. The first column is pressure, 5.9 megapascal, and go ahead and read nu F, which is value of nu for saturated liquid. And then when I have nu F, that's my nu 1. Divide volume at a state 1 by nu 1, and that gives me mass. Let's do that. See, it's kind of like reverse engineering. You say, okay, volume of the tank is volume of a state 2, which is mass of a state 2 multiplied by a specific volume of a state 2. That's the relationship between volume, mass, and a specific volume. You need volume, that's mass multiplied by a specific volume. That's volume of the tank, which is volume at a state 2. So that's going to be mass at a state 2, a specific volume at a state 2. But there is no need to say mass at state 2 is the same mass. So I need to find mass and I need to find a specific volume at state 2. Under a note, I wrote that volume divided by a specific volume is mass. So in order to find mass, we go back to a state 1 and we say, okay, mass is volume at state 1 divided by specific volume at state 1. I have volume at state 1. It's given 0.03 meter cubic, but I don't have a specific volume at state 1. So we refer to a table, because we know at state 1 is saturated situation, saturated liquid. So you need saturated table. It should be A12. It's not A13, A12, I think, because A11 and A12, there are saturated table. A11 starts with temperature, A12 starts with, pressure. So you go to, A12, and just give me a sec to finish that, then I'm taking question. Then I will take questions. So A12, please correct that. And, at the first column, go and find the pressure P1, which is 0.9 megapascal. Sometimes you can find it, sometimes you have to interpolate. So it's 0.9 megapascal, which is equal to 900 kilopascal. And nu 1, which is nu F, because it's saturated liquid. So nu 1 is nu F, and it is at 900 kilopascal. It's going to be 0.000858 kilojoule per kilogram. And then once I have nu 1, we plug in into this equation relationship between mass, volume, and a specific volume. Mass is volume divided by specific volume. We have the volume at a state 1.03 meter cubic divided by specific volume at a state 1. So mass going to be 34.96 kilogram, right? Once you have mass at a state 1, it's like you have mass at a state 2. It's the same mass. So here in this formula, volume of the tank is mass at the state 2, which is the same mass as the state 1 times nu 2. That's a relationship between volume, mass, and the specific volume when you're looking for volume. So we have mass. All we have to do is just find nu 2, a specific volume at a state 2. Now, let's see what information we have from a state 2. We know the pressure is 280 kilopascal and temperature is 20, which is 293. So remember I said whenever you don't know what is the state, your reference is always saturated table. So you go to saturated table and take it from there. So we go to saturated table for refrigerant. You can go to A11 or A12. A11 starts with temperature, A12 starts with pressure. We have them both. That is on page 916. I go to A11. And A11, because it's saturated table that starts with temperature, and I have temperature as 200 degrees centigrade. In the first column, find 200 degrees centigrade, and you find saturation pressure with pairs with it. That's 527.07 kilopascal. And you figure that's pressure of the substance, which is 200 degree kilopascal, is less than saturated pressure that pairs with temperature of the substance. Temperature of the substance is 20. Saturation pressure for that temperature based on saturated table is 500 something, and pressure of the substance is 280, which is way less than this, because pressure is less than saturated pressure for given temperature, which is temperature of the substance. You are dealing with superheated vapor. So let's go back to superheated vapor table, which is for refrigerant 134. That is table A13. That is on page 919. So you go to correct table now that you realize that it's superheated, but you always start with saturated table. That's your reference when you don't know what is the state. And as you know, it comes in the section. You find the section with the given pressure, which is pressure of the substance, 280 degree, which is 0.28 megapascal. In that section, the first column is temperature. Go ahead and find the row which says 20 degree, which reads 20 degrees centigrade, and go ahead. There are 3 columns, one for U, one for V, one for H of superheated. Value of those parameters was superheated under the given pressure and temperature. In the same row, go ahead and read nu, which is your nu2. And that is 0.07997 meter cubic per kilogram. Once you have that, you plug in back into this equation. You have nu2 and you have m, so you can calculate volume at state 2, which is basically volume of the tank because the whole thing occupies the tank. So all I did here, I just plug everything into this equation for mass and for nu2, and here is volume of the tank, 2.8 meter cubic. By the way, I also explain it on this diagram. See, if you take y-axis for pressure, x-axis can be anything, nu, u, h. In this case, it's nu. If you take y-axis as pressure, then we keep the temperature constant along this diagram, and it's this descending diagram. This part is for compressed liquid. This part is for superheated vapor. Here is saturated liquid. Here is saturated vapor. From here up to here, that is mixture of saturated liquid and saturated vapor, right? So we keep the temperature constant because y-axis is pressure. By keeping the temperature constant, that is the temperature of the substance, which is 20 degrees centigrade, right? Under 20 degrees centigrade, when you have this information about the substance and you don't know what is the state, and you start with saturated table, you go to saturated table, which starts with temperature, and at 20 degree centigrade, go ahead and read saturation pressure that pairs with it. You see that saturation pressure here, which pairs with 20, because from here up to here, it gives you saturation pressure. It's 527 something kilopascal is the unit. And pressure of the substance actually is 280, which is somewhere here, less than, below the saturation pressure for the given temperature, which is 20. So it's below. So you are dealing with superheated. Remember, I explained for all the points located on this part, which is superheated, the pressure, see, falls below saturation pressure, which comes with this given temperature, right? It falls below. See, here is saturation pressure for all the superheated, for all the points on superheated line, it falls below saturation pressure. And it makes sense because it's superheated. For superheated, the pressure is less than saturation pressure, but the temperature is higher than saturation temperature, right? Remember, I put it in different category, how to realize what that is. In case 1, 2, 3, 4, if, for example, nu is between nu F and nu G, then it's saturated mixture. If it's, greater than nu G, it's superheated, less than nu G. For U, for nu, for H, for P, for T. So I put it in different category. How to realize what is the state of the substance. You need 2 pieces of information. They may give you temperature and pressure, and I discussed that under the case 1 and 2, under the given temperature, under the given pressure. They may give you pressure or temperature and one of the property of the substance like U or H or V. So they may give you P and U, or T and U, or P and nu, or T and nu, or P and H, or T and H, or T and P. You need 2 pieces of information. I put it in different category 1, 2, 3, 4, 5. And I clearly and in detail explain it. Please refer to chapter 3. I see 2 students raise their hand, but previously I saw Matthew. I saw that you raised your hand. Do you still have your question? I hold you because I wanted to finish this part first, and then if you still have a question, you can ask. Matthew? Are you still there? Guys, can you hear me?
Yes.
Yeah.
Okay, good.
Yes.
I see two students, they raise your hand, and also the Matthew. If you have any question, you can ask your question.
I have a
How
quick
about
question, Professor, on the
your
second
name?
hand.
Yeah. Okay,
Peter.
please go. Yeah, Peter. Please
Um,
go ahead.
so this table over here that you the PV PNU diagram, do you expect to see this from us as well on the exam for credit, or is
No.
this just for our reference?
If I ask you, then yes. If I don't, no. But it's always helpful, for you. I just brought it here to be able to explain it better, and it's kind of like a review. But if I don't ask you, no, you don't have to. But my advice would be try to have it, on your paper, somewhere. It's helpful. It gives you some insight, some idea what you are doing. But no,
Thank you, Professor.
sure. Any other question, guys, you may have? All right, then. If you don't have any question, you're almost done. So I just have this review. It's better than nothing, right? And thank you for you guys to come. Let me stop sharing, and I'm going to take enrollment. All right, just give me a sec. So I'm going to a screenshot. Just give me a sec. Bring the screen. Okay. All right. Stay put for a second. Okay. This. Okay. Oh, I already also recorded, so I'm still recording. All right. So I have everything here, everything I need. Okay, do you have any question, guys?
Should we expect like one question from each chapter, or is it going to be like more chapter 3 heavy?
What was your question again?
Should we like
Oh, okay, I see. You're asking if you have, see, usually it's combined questions. So it's not like, so you have to use information from chapter 3, maybe. Remember this example, for example, turbine example, or so you may use, chapter 3 along with, chapter 2, so it's usually combined. But I'm going to test you on all 3 chapters, of course, it's not focused on just one chapter, All right, did I answer your question?
Yeah.
Okay. And I'm gonna send the slideshow to you, the non-audio version right after this via email. So you are gonna have that, and that's it. I see Alan, you raise your hand. You have a question?
Oh, no, that was my question. I was going to ask if you're going to email the review to us.
Yeah, I'm gonna email the review, but not non-audio version. So
Okay.
yeah,
All right,
but you
thank
can, if you already recorded, you can share it with your friends, Peter, you have a question?
Yeah. I'm not sure how difficult it is to share the screen again, but I do have a question on the oil pump example, if it's
Okay,
possible.
I can share the screen. Why not?
It
Let
should
me
be
share the
fast.
screen and let me go to, you said the oil problem.
Correct. That should be the third example, I believe.
All right, here. It's about
Yeah,
here.
this one. Okay, so I
Mhm.
think the second page, if you could go one more.
Sure, the second page. Yeah.
Oh, actually, sorry, one more
One
page
more.
after
All
this
right.
one. Yes.
Okay, sure.
Okay, yeah, this one. So I was looking over this. I just wanted to like double check and see like how you went from, the change in electrical energy equals mass flow rate times whatever. So I know the 0.1 came from the mass flow rate. I'm trying to figure
Yes.
out what the
You are
rest
you are
here is.
you are thinking between these two?
Correct, yes.
Okay. See, mass flow rate is density times volume flow rate, right? If you refer to your notes from chapter 2, you see both version. So I started with this one, then I go ahead and I wrote, okay, mass flow rate is density times volume flow rate. And I kept the volume flow rate outside the bracket and multiplied the density by the terms in the bracket. So when you write m dot is rho v dot, keep v dot outside and multiply rho by each term. So when you multiply by this one, rho cancel out. So you're going to have P1 minus P2, right? And then when you multiply this by rho appears here. So it's going to be half of rho P2 squared minus V1 squared. This is
It should be at
multiplication.
times. Okay, that's
Yeah, it
multiplication.
is time. Yeah, I
That's the
mentioned
only
that.
thing I was
Yeah.
confused. Okay,
Yeah,
okay.
it was multiplication. I just wrote it this way, but it's multiplication. And then when you multiply rho by G, it's gamma, which is a specific weight. But in this case, it's this term goes away because there is no, change in elevation. But yes, that is multiplication.
That makes perfect sense. Okay, now it all makes sense. Thank you, Professor. I
Yeah,
appreciate that.
Of course. Is there another question, guys? Before I stop sharing? Yes, Leonardo, please go ahead.
Oh, sorry. Just to add on to that. So we multiply that by the density, is that correct?
Yes, exactly. That's the density. It's half of rho V2 squared minus V1 squared. Exactly.
Okay, yeah, I see it now. Thank you.
Sure. Any other question? All right, I'm gonna stop sharing and we're done. If you don't have any question, we can leave the meeting. But if you have any question, I can stay.
Awesome. Thank you very much, Professor.
Have a good evening.
You
Thank
too.
you,
Professor.
Thank you, Professor.
Thank you, Professor.
Thank you, guys. Thank you. Thank you.
Professor, will you take like any kind of attendance, or how will you know who to give the
I
points
recorded the session. Yeah, I recorded
Okay,
the
okay.
session. I a screenshot.
Okay.
So yeah.
All right.
I was
Thank
a
you.
little bit late.
What's that?
I was a little bit late. I couldn't make it on time. But
Yeah, I have the whole session recorded, and I also took the screenshot. So I have everything. So
yeah, I'm afraid that when you took the screenshot, it was before I came.
that's you, Maria.
Yes.
So I remember. Yeah, you attended the session. Okay. All right. Anyone has a question? Someone is not muted, so I cannot. Is there anyone who has a question? All right, then. I'm gonna end the meeting.